All right, so how do we take what we learned yesterday and apply it to what we're doing today? Okay, so yesterday we talked about the difference between if you have an exponential model versus having a power model. And the way that you can tell is with an exponential model, you will have a log with your y value, and then everything else will just be numbers. With the power model, you'll have a log on your y value, and then on the other side, you will also have some number associated with a log of the x value. So exponentials just have a log on y, and power functions have a log on x. Excuse me. Of course, that's going to happen. Power functions are going to have a log on the y as well as the x. Okay, so if we're looking at example 2, example 2 says, what is the relationship between per capita income in a country and child mortality? On this page is computer outputs for 3 different regression models examining this relationship for countries in Central and South America. So child mortality is measured in deaths before age 5 per 1,000 children born, and income is measured in US dollars per person. Questions about these data are on the next page. All logarithms are base 10. So if we're looking at this, so the first model that they did is just child mortality versus income. If you look on the scatter plot, I don't see any logs whatsoever. So this data has not been manipulated. It has not been scaled. It's just your regular data. Okay. If we scroll down to the next section, it says log of child mortality versus income. So if you notice, we've got a log on the y-axis, but we don't have a log on the x-axis. So that tells us that that is an exponential model. We still have a little bit of a curve, but it definitely looks more linear than the problem that was above it. The problem above it looks like it's pretty curved. Okay. So as we scroll down a little bit more, number 3 has log of child mortality versus log of income. So if you notice, there's 2 logs. We got a log on the y-axis. We got a log on the x-axis. That's proving that this is done using a power model. And if we look at the scatter plot, this scatter plot looks really linear. So out of all these 3 distributions, that power model is the one that's going to fit the best. Okay, so we are going to use this data table, and we're going to use all of this information to run our regressions. So number 1, explain why the information provided suggests that a linear model might not be appropriate for describing that relationship. Well, linear model isn't appropriate because if you look at the first model, that scatter plot didn't have a linear strength. If you look at the residuals, even these residuals kind of have a nice curve pattern. Okay, so we just have to identify that in the problem. We'll say the scatter plot relating child mortality and income shows a curve pattern. And we could say the residual plot also has a curve pattern. So why a linear model won't work? Because it's not linear. All right, number 2. It says, would an exponential model or a power model provide a better description for this relationship? Okay, so what we can say is, we'll say a power model, because that was the more linear relationship between the two. And we will just write the scatter plot relating log of child mortality and log of income shows the strongest linear pattern. Therefore, a power model is the most appropriate. Okay, so now here's the new part. It says, give the equation of the model you choose in question 2 using transformed variables. Okay, so like I said, we are going to be using this table. Probably going to write this equation up top. Okay, so our normal equation looks like y hat equals a plus bx, right? All right, so here's our y-intercept. Here is our slope. Okay, but because we have a log on the y and the x-axis, we now have to transform this to say log of y hat equals a plus b log of x. Okay, and we're supposed to have a log on both of our variables. Okay, so I've got a y-intercept of 2.9649. All right, so this would be, sorry, give me a second. This would be log of y hat is equal to your y-intercept, which was 2.9649, plus your b value, your slope. Let's go back up to the slope so we can see it. Is negative 0.468. I'm just going to round a little bit. Negative 0.46824. Let's see if I can remember it. Negative 0.46824 log of x. Okay? So there's your function. You write it the same exact way that you would normally, but you put a log by the x and a log by the x and a log by the y. All right, it says, use the model you chose in question 2 to predict child mortality rate in the country with an income of $1,300 per person. You show your work. Okay, so here's your amount. This is a dollar amount. So if we look at all of our scatter plots, the dollar amount always was on the x-axis, right? The income was an x value. So they gave us an x value. So we're going to substitute that in for x. So log of y hat is equal to 2.9649 minus 0.46824 log, and then we put in our x value of 1,300. And now we got to remember something about solving logs. This whole right side is just numerical. Okay, so we can type this into our calculator. So bring the calculator up, type it in, 2.9649 minus 0.46824 log of 1,300. Push enter. I get 1.5068. And now we have to remember we have to solve for y. I don't want to have log in there. Okay, so log without a base is technically a base of 10. And if we remember, to get rid of a log, we have to transform it to exponential. We start with our base, which is 10, go around to the exponent, which is 1.5068, and then set that equal to our argument, which is y hat. Okay, so I have to do 10 raised to this number. So here's that number here. So I'm going to do 10 raised to that number. Push enter, and I get about 32.12. Okay, so this is my y hat. This is my predicted child mortality. What does that number actually mean? Well, if you go up to the top again and we look at the explanation, it says child mortality is measured in deaths before age 5 per 1,000 children born. Okay, so this is 4-year-olds and less. So technically what this means is where families make $1,300 per person, you're going to have 32 kids ages 4 and under die out of every 1,000, which is quite a bit of children. So 32.12 per 1,000 children die in this country before age 5. Which is a kind of a scary note to have, but that's how we interpret this question. For you guys, we also have to remember sometimes they won't do a log with a base of 10. Sometimes they use a natural log. Okay, so if you're ever using a natural log, let's say I've got natural log of y hat is equal to, I don't know, some number. We'd set it up like 4.6. Just in case this happens, they don't always use a regular log. Sometimes they use a natural log. To get rid of a natural log, we use e. So we're going to take e to both sides in this case. Okay, so e to the natural log of y just becomes y hat. Right? We kind of say those two things undo each other or cancel each other out. And on the right side, you have to do e raised to the 4.6. So if I went e raised to the 4.6, I would get 99.48. All right, so just a little bit of side help just in case we're working with natural logs instead of regular logs. Okay, that's it. You guys can go ahead and get started on your homework, and I will see you tomorrow.